Hello, my friend. Welcome to my new lecture. This will be about transporting packets with the IP through IP. So you learn very important concepts to understand what is this internet, how this IP package is controlling with the things, with the technologies, so with the protocols. You'll understand all this stuff with me, okay? Just we'll go step by step and you'll understand everything in the good way. Let's start with me. The problems with packets, that is our first topic. We'll understand what will be there. So I occasionally thinking like how we can solve this problem because generally I know how to solve. So let's go step by step what we'll do there. Really, it will be helpful. I'm sorry, I mean, at one point, I was came here for make these videos because I had been on the way. It was late, and I just came here. I didn't go to my place, so on the place. Well, let's start it, guys. The Internet Protocol IP describes how to split messages into multiple IP packets, opens in a new window, and route packets to their destination by hopping from router to router. IP does not handle all the consequences of packets. However, for example, a computer might send multiple messages to a destination, and the destination needs to identify which packets belong to which message. That's cool, cool information. Oh, I think I was being very fast. Let's go step by step. Okay, let's look here. Packets can arrive out of order. That can happen, especially two packets follow different paths to the destination. Well, it's okay. Packets can be corrupted, so really it can be, which means that for some reason the received data no longer match the originally sent data read. It can be so packets can be lost due to problems in the physical layer or in routers forwarding tables, which is I showed you. If even if even one package of a message is lost, it may be possible to put the message back together in a way that makes sense. Similarly, packets might be duplicated due to accidental retransmission of the same package. Well, just calm down. What I'm explaining to you, you'll understand all this concept. Fortunately, there are higher level protocols in the Internet protocol stack that can deal with these problems, which as we're calling it, like the first one is Transmission Control Protocol, which is TCP. This is very multifunctional. It will help for corrupted, so for the not far to about corrupted, lost, duplicated, all the situation is the data transport protocols that's most commonly used on top of IP, and it includes, which is we're calling it like metadata, uh, for sending normal data, and so it's just we're doing some editing there like that, or we just reporting everything and it's going data way. Well, we'll talk about it, okay? IPN it includes strategies for package ordering, retransmission, and data integrity. So, user datagram protocol, which is UDP, is just for one function. It's just checking for uh, corrupted messages, data. You can think like that, which is I'm talking about. So you have some calculation for detect what problem between, or it can recognize. So the the receiver tagging true message, correct message, or wrong message. It can compare it with some way, but it's not multifunctional and it's just security, so protectional. Okay, so TCP is better than so generally we're calling it like TCP/IP with this way. Internet application can choose the data transport protocol that makes the most sense for their application. Okay, Next article will explore TCP and UDP in more details. We'll just come. Let's start with user datagram protocol. Okay, let's do it with me. What is this problem here? Let's do it. Keep right. Uh, slow, slow, slow. Okay. The User Datagram Protocol (UDP) is a lightweight data transfer protocol that works on top of IP. UDP, which is User Datagram Protocol, provides a mechanism to detect corrupt data in packets, but it does not attempt to solve other problems that arise with packets. So it's just working for that. So such as lost or out of order packets, that's why UDP is sometimes known as the unreliable data protocol, which as I told you, you can't trust it. You can't trust it. You can't trust it, or which accent will be good for you. So let's say UDP is simple but fast, at least in comparison to other protocols that work over IP. It's often used for time-sensitive applications. So for UDP, time is important than data. Okay, just it want to go very fast. It want to bring information or data very fast. It's not interesting with too much with the file with the data is true or bad or so it's not all about it. It's just going very fast. Okay, it's bringing information very fast, sending. So for him, just receiver important and fast important, speed important. So let's say such as real-time video streaming. Yeah, for that. So where speed is more important than accuracy. I told you. For that, they are saying unreliable system. Package format. Right. Yeah. Oh, yes. Maybe. Yeah. Right. When sending packets using UDP over IP, when sending packets using UDP over IP, the data of portion of each IP package opens in a new window. It's okay. It's formatted as a UDP segment. You can understand this point is very important. UDP over IP, data portion of each IP package. For each IP package is opening their new page, new window for UDP segment. So we have here source port number, destination port number, and segment length and checksum. Will will understand this checksum how working there because it's bringing data there and it's just parsing it, separating it, and calculating it if it is true from sender to receiver between them. So it is true. So let's calm down. No, what happened? Okay. Yes, each UDP segment contains an 8-byte header and variable length data. So it's calling about that. So source port numbers will be 4. So then we have 2 here. Segment length will be 2, and checksum will be 2 byte, and it's totally 8 byte. Okay. Let's look for port numbers. Okay, let's start with port numbers. The first 4 bytes. Oh, what happened? Read it. Please. Yes, here. The first 4 bytes of the UDP header store the port numbers. I mean, for the source and destination, this 2 and 2 like that. A network device can receive messages on different virtual ports, similar to how an ocean harbor can receive boats on different ports. The different ports have distinguished different types of network traffic. Here's a listing of some ports in use by UDP on my laptop. So you can check it if you want. You can write also this if you are using Linux system and Ubuntu or another parent or I don't know. So another system, then you can check it. Okay, operating system, I mean. So you can write list of, like sudo list of, and I and minus me and minus p, and you can write grep udp. You can check udp there. This will be port numbers there for indicating, then it will be your things there. So you can see then IPv4, IPv6 alternative, so you can understand which kind of hierarchy are there too. So let's say each row starts with the name of the process that's using the port and ends with the protocol and port number. Protocol and port number, right? Protocol IPv6 or IPv4, and port number will be there, something. So what sort of network traffic did those process handle? If you search the web for the process name plus the port number, you can probably figure it out. You could even try it on the computer you're using now. So segment length. So we understood now sort destination. So sort port number and destination port number. Now, so four byte is gone already. So now we'll start to look for the reminder two. So 4 byte, what is it? Segment length is just tagging 2 byte. Let's look what is this details there about it. Okay, let's come a little faster here. Okay, the next 2 bytes of the UDP header store the length in bytes of the segment, including the header. So this header, 2 bytes in 16 bits. So the length can be as high as this binary number. In decimal, that's to 16 power of 2 minus 1 is like 65,535. Thus, the maximum length of a UDP segment is 65,535 bytes. There, about maximum length of a UDP segment. Okay, checksum. This is important point. How this comparing data there, if it is true. So if our data corrupted or not corrupted. Okay, checksum. The final 2 bytes. Let's go a little left here. The final, let's go a little right. I just want to put, yeah. I don't know why it's like that. Let's go a little right, maybe. Yeah, the final 2 bytes of the UDP header is the checksum field to before sending of the segment the sender. So let's do one. The first step computes the checksum based on the data in the segment. Second, the two stores the computer checksum in the field, right? Upon receiving upon receiving the segment recipient, so this is recipient part, this one is sending part. Okay, computes the checksum based on the receiving segment, compares the checksums to each other if the checksums true, like that. So let's look at it. Aren't equal, it knows the data was corrupted. So I think here we don't have more information. Yeah, segment only there. Okay, so that's that. It's just checking. I told you. To understand how a checksum can detect corrupted data, let's follow the process to compute a checksum for a very short string of data, hola. Okay, let's do it. So first, the sender would encode hola into binary. Somehow, the following encoding uses the ASCII, which is ASCII code, UTF-8 package. Okay, encoding package. Let's come here. The age is like that, O is like that, and our bits here, so bytes here. So it's just 4 bytes. So that encoding gives this 4 bytes I told you. So this our bytes here, the correctly here. Let's say next the sender segments the bytes into 2 bytes. So the sender segments the bytes into 2 bytes 16-bit binary numbers. It's just like that. It's just bringing ho and la, so down and above, like ho will be above, la will be down. Then it will calculate like 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 sum. You just sometimes you're calculating. It's like that. To compute the checksum, the sender adds up to 16-bit binary numbers. It's like that. Then it's calculating. How they add binary numbers? How they doing it? Do you know? So if you want, I can explain you that. Let's do. 1 and 1, it's making 2. So we're representing 2 in binary system like this. The first one is representing 0 power of 2, and second one representing 1 power of 2, right? It's making 2. So if you say this 2, it will give us 0 here, and we have here remainder 1, right? Then look on another one. It's 1, 0, and we have here also 1. It's 2. Now again, it will be 10 like 2. So here like binary system. In decimal we have same system. Really, just don't worry, just calculate with the binary system. Then we have again 0, 0 we putting there, and we have 1. Let's go here. We have again 1, and this going like that. And here we have 1. Let's look here. 1 is going there, and we have again 1, and it's going 1. Again we have 1 here, and we have 1, and here we have 0, 0 here, and here 0. So it's 2 0, and we have 1. It will be 1. But if we say 1 will be like that, let's check it's coming like what. So if we have only 1, what it will be? Let's just think about it. Only 1. How we representing only 1 in binary system? What do you think? You need to understand one thing here. We have 1, but we have 0 here too, right? 1 plus 0 plus 0, it will be just 10 again, like that, right? We'll put there this 0, okay? Just try to understand. The logic is basic here, okay? To understand every concept of this thing. So calculation. Because it's here, the point like that. 1, 0, and 0. If you check normally, we have 1 there, right? But if you bring 1 to 1, it will be 2. In 2, in binary system, we're representing like that, like 10. And we put in 0 there, and reminder 1, we're going on. But if we have only 1 here, what we need to think? We have only 1, just think. What we can do with the 1, only 1. So yeah, you need to get it, get this point. So it's this here, we're calling this point. So this point with this point, it's again same. I think you got it. So just point is that I told you, listen carefully. If we have 1, 1, 1, and 0, we have 3, 1, right? What is it? 3. In binary system, we're representing 3 like what? Like that. Look, it is just like that. 1, 1, right? It's like that. So then we need to put here like that. 1, and we have 1. And we will go left side. And if we have here 0, 0, 0, or let's say 1 again, then we have also 1, 1. So 1. Also, it will be, if we calculate 2, it will be in binary system like 10. Then we will put here 0, and we'll put 1. The remainder part will go like that. I think you got it. I hope you got it. Okay. So the computer can now send the UDP segment with the encoded HOLA as the data, and like that as the checksum. The entire UDP segment could look like this that I showed you. So source port number is 2 byte, and destination port number is 2 byte. Length will be 2 byte again, like I mean it can tag 65,535. The header, I mean for the disk. So checksum will calculate this data first point, ho and la here, and we will checksum and it will give us the correct solution. So then we can send data to another person. Receiver can take it. I mean, so let's count down. What if the data got corrupted from hola to mola on the way? First, let's see what the corrupted data would look like in binary, mola encoded into binary. So this is mola. This is not hola. This is mola. Just our age is different here. And then segmented into 16-bit numbers. Now what it will be, it will calculate again this way. Now let's see what checksum the recipient will compute. So it will again calculate like this way, and this will give us different solution of this calculation. So then our data will be corrupted, right? Corrupted. But what I told you, it can be very dangerous. So it's just, UDP looking for speed than accuracy. So it can sometimes send this wrong data, false data. The recipient can now programmatically compare the checksum they received in the UDP segment with the checksum they just computed, like that. Receive it and compute it. So it's different. It's different. It's not like same computed is different received. Do you see the difference? Make it obvious. I think you see. When the recipient discovers that the two checksums are different, it knows that the data was corrupted somehow along the way. Unfortunately, the recipient cannot use the computer checksum to reconstruct the original data, so it will likely just discard the package entirely. The actual UDP checksum computation process includes a fair more steps than shown here, but this is the general process of how we can use checksums or detect corrupted data, right? It's like that. So, I think you got it. Let's start for transmission control, TCP. This is very important than other. Okay, let's start with it. What we learn. The Transmission Control Protocol (TCP) is a transport protocol that is used on top of IP to ensure reliable transmission of packets. Right? It's very so relying. You can rely it. So it's more trust than others. So TCP includes mechanisms to solve many of the problems. Many of the problems that arise from package based messaging such as lost packets, out of order packets, duplicate packets, and corrupted packets. It's more functional, okay? We can take our pencil, let's say duplicate packets, out of order packets, because it's very important protocol. Yeah, out of order, such as lost here, also lost tab, and what we have corrupted too is 4. Okay. So, since TCP is the protocol used most commonly on top of the IP, the Internet Protocol Stack is sometimes referred to as TCP/IP. Okay, let's come here. Let's start with package format. Let's look what is that. Um, yeah, let's go to the left. Yeah. Okay. When sending packets using TCP/IP, the data portion of each IP package opens in an even though again like that is formatted as a TCP segment like UDP segment, but something different in that point. Source port number is same, destination port number is same, but we have here sequence number and acknowledgement number. Really, it's this communication better than other protocols, which is I'm talking about TCP better than UDP because it's more functional for protection and they have some good communication for accuracy. Each TCP segment contains a header and data. The TCP header contains many more fields than the UDP header and can range in size from 20 to 60 bytes depending on the size of the option fields, right? The TCP header shares some fields with the UDP header, right? Source port number, destination port number, and the checksum to remember how those are used to review the UDP article. So you can check it again. So from start to finish, let's look what steps will be there. The steps through the process of transmitting a package with TCP/IP. So step one, establish connection. Right, the first step is that important than others. What happened? Let's go up. Okay. When two computers want to send data to each other over TCP, they first need to establish a connection using a three-way handshake. Right. This is very important. Synchronization, sending one synchronization, and another one saying knowledge, and sending another synchronization, and another one saying it and saying accuracy is true. So I mean, our communication is true. So just there ensuring it like that, and check we're calling it. The first computer the first computer sends a package with the sync, which is we saying synchronization. So bit set to one like synchronize. The second computer sends back a package with the ACK, like that, like we calling it knowledge plus the same like bit set to first, like the first computer replies back with a knowledge again, so just for the accuracy for the connection. The sync synchronization and knowledge bits are both part of the TCP header. This is very good communication model. So I mean this point and all the number sequence now is just applying and sending this point anyway. So we'll see all of that. Okay. Let's look. In fact, the three packets involved in the three-way handshake do not typically include any data. Once the computers are done with the handshake, they are ready to receive packets containing actual data. Step 2, send packets of data. Alright, this is step 2, send packets of data. When a package of data is sent over TCP, the recipient must always acknowledge that what they received. Let's look here. We have sequence here. This data, it's the number of this not a knowledge, synchronization. It's going with the number of the knowledge, I think, right? And it's saying 37. So knowledge is 37. It's sending this one with the one is saying 37. So the first computer sends a package with data and a sequence number, right? Sequence number. The second computer acknowledges by setting the acknowledge with an increasing the acknowledgement number by the length of the received data. The sequence and acknowledgement numbers are part of the TCP header. Let's come here. What we're saying here, we'll understand better. So here I'm calling it like sequence number, acknowledgement number. It's just checking this one saying one, another one saying 37, but there is some problem because it has to send 37 and it can take 37, like they can communicate there together. Those two numbers help the computers to keep track of which data was successfully received, which data was lost, and which data was accidentally sent twice. Okay, step 3, close the connection. Either computer can close the connection when they no longer want to send or receive data. It's okay. The first saying finish, it's sending synchronization finish. The another one saying oh okay, acknowledge, just sending again finish, like it's okay, I'm okay like that. So the sender computer saying acknowledge. So the close, we can close now. I mean, if there is no data or no sending. So the computer initiates closing the connection by sending a package with the fin. So it's representing like that fin. Bit set to finish. The order computer replies with an acknowledge and another fin. After one more acknowledge from the initiating computer, the connection is closed. Detecting lost packets. Okay, detecting lost packets. Like what? TCP connections can detect lost packets using a time. Oh, this is very good. It's sending one, the sequence number one, this data, and at the same time it's sending another sequence one. At the same time it's doing that, there's some alarm like saying It's saying, so after sending off a package, the sender starts a timer and puts the package in the retransmission queue. If the timer runs out and the sender has not yet received an knowledge from the recipient, it sends the package again. Yeah, it's just duplicating too much, but yeah, just don't worry. It can send multiple messages at the same time and same message, but yeah, this is better than nothing. Okay. Direct transmission may lead to the recipient receiving duplicate packets if a package was not actually lost but just very slow to arrive or be acknowledged. If so, the recipient can simply discard the duplicate packets. It's better to have the data twice than not at all. Here, let's look handling out of order packets. This is also very good system. I mean, the TCP connections can detect out of order packets by using the sequence and acknowledgement numbers. Like what? Saying sequence 1, the sequence number is 1, the acknowledge saying 37. Then another one sending 73, and it's saying no, it had to be 37. Sending back to 37. Yeah, there have some problem about it, right? Because sequence is not true. Its data is wrong. Let's come down. When the recipient sees a higher sequence number than what they have knowledge so far, they know what they are missing, or at least a package in between. In the situation pictured above, the recipient sees a sequence number 72 but expected the sequence number 37. The recipient lets the sender know there is something amiss by sending a package with an acknowledgement number set to the expected sequence number. Sometimes amazing packages simply taking a slower route through the internet and arrive soon after. Well, I'm talking about that. Let's check it. The sequence, the sending sequence one is saying it's saying acknowledge, it's saying acknowledge synchronize it, so it's saying oh it's okay, it's 37. Then it's sending 73, and this one's saying no, it's 37, it's not 73, and it's sending again 37 there. So at the same time, it's sending 37 and 73. So there are some corrupt packages, right? So it's just trying to solve this problem. It's just coming two package here, like wrong. And so other times the missing packet may actually be a lost package, and the sender must retransmit the package. I'm talking about that. So sequence one, 37, synchronize and sending send. So 37. And at the same time, 73, but 73 is a corrupt packet. It's not true packets. That's the 37 is going, but it's just staying here because it's not going like that. So the problem is starting there for that point. Let's say in both situations, the recipient has to deal with out of order packets. Fortunately, the recipient can use the sequence numbers to resemble the package data in the correct order. Sometimes we can visualize it like that. So sequence one is going there. So the sequence 73 it can connect it to the 73 later, so it can prepare the situation. So 37, 37 is matching there. So let's come practice questions. Transporting packets. Practice question. Let's start with here. Take pencil. One problem with package-based messaging system like the Internet Protocol is that packets might arrive out of order. Okay, the TCP is a protocol that can deal with out-of-order package. When used over IP, each package contains a TCP segment with metadata and data. Which of the following best describes the TCP can resemble out-of-order package? Okay, let's say what we have here. The TCP metadata and data can be combined to figure out where that package belongs in the segment. A separate package received after all package with data has arrived contains information on the sequence of the data package. The TCP metadata includes fields that describe where the package belongs in the sequence. The TCP data includes information. The TCP data includes information at the beginning that describes where the package belongs in the sequence. So here, the TCP metadata and data can be combined to figure out where that packet belongs in the sequence, and this one, a separate package, so received after all the package with data is arrived, contains information on the sequence of the data package. This one, the TCP metadata, includes fields that describe where the package belongs in the sequence. That one is true. If you think, will you think it is like that? What do you think? Was I the true? Where the package belongs in the sequence? It's just where package. And also we have sequence of data packets contains information. What do you think? What do you think? Think all about them. I said this. What do you think? It's A, B, D, can be? I'm just I'm just arbitrarily selected. What do you think? Rafi is developing an application to send urgent information about global health crisis over the internet to his hospitals. He's worried about packets getting lost along the way and the fact that will have on the accuracy of the information. What is the best option for dealing with lost packets? Rafi, let's say Rafi can use transmission control protocol for communication since TCP has ways to recover when packets are lost. Rafi can use the transmission control protocol for communication since TCP prevents packets from getting lost. Rafi can use the internet protocol communication since that includes a mechanism to recover data from the packets. Rafi can use transmission control protocol for communication since TCP has ways to recover when the package, right, recover it. You can recover, right? What do you think? It's true? It cannot be true, maybe, right? Just go check it. What do you think? Maybe it's true. TCP prevents packets. I know answer really. So just I'm I'm just trying to blow your mind. What do you think? Recover data. It's from lost packets. This one is when using IP, it's something like that. What do you think? Let's like and write in comment, in description. The last one is what? What is the no? It's here. The following table compares the two data transport protocols from the suite of protocols powering the internet. Can it handle? Protocol one is UDP. Protocol 2 is TCP. Okay? Because I know it. You need to know too. You didn't say anything more. So, current package. It's only so it's in UDP we have this right in UDP. It's a special for UDP because it's just looking for speed too much. Yeah, but it's just also looking for correct packets. But the speed very important than this. And protocol 2, which is TCP, has already this specialization, I don't so specialization. I mean, specialization. I don't know specialization. I don't know how to use it. Anyway, lost packets, it's don't have for the UDP. Okay, it's no, of course. It's not multifunctional, and we have here, right? For the TCP, we have this. Out of order packets, it's no, of course, for here, and we have for this point. So, what are the most likely identities of protocol one and protocol two? So we know already what we are talking about. So just to describe it. So protocol one explaining UDP and protocol two explaining TCP. That one is true. It's not. Oh, let's check if I'm not wrong. Yeah. So that's correct answer. Okay. Maybe it can be this. I can. Maybe I'm blowing your mind. What do you think? Let's do TCP can be IP. What do you think IP can be? Our another topic will be web protocols, the wide web. This is very important. Every day you see it in internet, but you don't know maybe what is it. So we can check it together. We're going details, okay? Um, what we learned today, we did something with it. So come up. Right here, right here. Transporting packets today. Our topic it's finished. Thank you for joining. Another lecture. Next lecture will be about the World Wide Web. Thank you. Have a good day.